Let me correct something I said on the last video, and it's amazing how you can say something thinking that you said something else, and then you go back and watch what you actually said, and you're like, wow, I can't believe I said that. But anyway, what I said was that step 1 here, and the steps that we were looking at for what's going on from the presynaptic to the postsynaptic, step 1 was actually the action potential coming down and opening up, these calcium gates. And I think what I said was neurotransmitter coming in and opening them up. But neurotransmitters obviously have nothing to do with what's going on with the action potential here. The neurotransmitters I was talking about before would have been what would have caused threshold, which would have generated the action potential. So anyway, what I meant to say was the action potential comes down through the axon to the axon bulb and then opens up the calcium channels. I hope that's clear. And I played the video right after I said that, and of course they said the correct thing in the video. So I hope that didn't confuse anybody, but let me know if you're not sure what I was talking about. Okay, we said acetylcholine, which has cholinergic receptors, and here were 2 of the 3 examples we're going to look at. Of course, we said there were receptors like we find in the neuromuscular junction, which were direct and fast. Then we said there are excitatory receptors, cholinergic receptors, that we would find in our central nervous system. But what I didn't tell you last time is I want to point out they're also found on our parasympathetic effector organs. So remember, our parasympathetic nervous system is designed to put us back in the rest and digest state of being, as opposed to the fight or flight state of being. Okay, so those effector organs, the ones that would receive the neurotransmitter, are going to have these indirect slow receptors on them. And of course, what they do is they receive the neurotransmitter, then they send a sequence of events that opens or closes channels, ion channels. Now, but in this case, they are excitatory, because especially here in the nervous system, we're being excitatory, so we can raise the voltage here at the axon hillock to threshold and actually cause that to send an action potential. Okay, but it is a slow. Why is it slow? Because it's not direct. It's slow, but it is excitatory, just like that's excitatory. So when would acetylcholine, when would it be indirect but inhibitory? That's what we're going to look at next. Okay, a good example of this is our heart has the ability to beat without neural stimulus, unlike other muscles, but it does have neural stimulus, and the neural stimulus is for the sympathetic or parasympathetic nervous system. Now, when we are in a sympathetic state, then this nerve here, which is that cranial nerve, the vagus nerve that we talked about, which was cranial nerve number 10, it releases acetylcholine to receptors that are found on the heart, and instead of exciting the muscle like the direct fast did, what this does is this actually inhibits or slows the heart rate down. This is important because if something interfered with this vagus nerve releasing acetylcholine at the indirect slow receptors here, then the heart would automatically speed up. So if somebody had nerve damage to that vagus nerve, their heart might automatically just start speeding up for no reason. Okay, but if we're in emergency, obviously we want our heart to speed up. So we have something called a cardiac nerve that is speeding the heart up. But this nerve then would be overridden. But once we are out of the emergency, we don't want the heart to keep racing. So this nerve then would start doing its job, releasing the acetylcholine to the inhibitory receptors, the cholinergic receptors, and it would actually inhibit and slow the heart down. So in this case, it would decrease our heart rate. So that's really important. So bottom line is the action of the acetylcholine can be either excitatory or inhibitory. What determines what it is the kind of receptors and where they are. Okay, another important neurotransmitter that can also be a hormone that's released is epinephrine and norepinephrine. Here we see norepinephrine. Okay, now epinephrine and norepinephrine is actually what we would call are the chemicals that make up adrenaline. So the receptors for norepinephrine would be instead of being cholinergic, they'd be adrenergic. And you can see I've got these 3 different receptors here, alpha 1, beta 1, and beta 2 receptors. These are adrenergic receptors that will only bond with norepinephrine. Okay, so notice again the adrenergic is adrenaline. Norepinephrine is part of adrenaline. Okay, and we're going to find both the alpha and the beta on our central nervous system and on our effector organs of our sympathetic nervous system, the fight or flight situation that we run into. Because when is norepinephrine released? Well, primarily during emergencies, during the times we need to activate our sympathetic nervous system. Now notice when norepinephrine goes to an alpha 1 receptor, then this is actually, then in this case, it's going to be excitatory, because what it's going to do, these receptors are going to cause smooth muscle to basically constrict our blood vessels. Now, when would you want to constrict your blood vessels? Well, when you either want to increase pressure or you want to kind of shut off blood supply to an area. Now look, where would I find these type of receptors on blood vessels? Well, I would find them in these areas, my skin, my mucosa, and my abdominal viscera. In other words, the abdominal organs. All right, now, so when I'm in a rest or digest situation, I'm sending a lot of blood to these areas. But when I'm in a fight or flight situation, I don't want blood sent to my skin, to my mucosa, or to my abdominal viscera. I want that blood sent to my skeletal muscles to help me get through that emergency. So when we shut off blood to the skin, people often turn pale. You know, when you get the blood shut off to your abdominal viscera, you don't have an appetite because you don't have a big ability to reabsorb the food. So when norepinephrine is excitatory, then one area it's going to go to is to the blood vessels going to these areas where I don't really need blood, and it's going to be excitatory because it's going to cause the smooth muscles to contract and constrict the blood flow to those areas. Here we see the blood vessel constricted, therefore these areas are going to have less blood in them because I don't need most of my blood going to them in the emergency. Again, that's why people get pale when they get an emergency many times. Now I have beta 1 receptors in the heart, and when norepinephrine gets to the heart, then that's going to be excitatory because it's going to, and it's slow excitatory. Notice none of these are direct, all these are indirect, meaning that they do have a sequence of events before they open the ion channels. But as far as the effect, then what this is going to actually do is going to be excitatory, which is going to literally cause the heart to beat faster. And we all know that if we're in an emergency, we want our heart to beat faster. If we're scared, we got a lot of adrenaline in our system, then naturally our heart is going to beat faster in this excitatory response because of beta 1 receptors. Now, you might have even heard of beta blockers before, where there are medicines that will block this binding. Now, we also have beta 2 receptors, which are found in blood vessels.
Acts indirectly at beta 2 receptors.
Okay, so it's acting indirectly, but it's also going to be inhibitory. And where are my beta 2 receptors? Well, notice.
It's a slow inhibition. This causes.
Okay, notice that I'm going to have the beta 2 receptors on certain blood vessels. Now, where do I want blood going in an emergency? Well, I want them going to my skeletal muscles. I want them to go to the blood vessels in my heart that get more blood to my skeletal muscles and get more blood to my heart. So even these what's called coronary blood vessels that are taking blood back to the heart tissue itself are going to be beta 2, but the muscles that are contracting are going to be beta 1. Okay, but the blood vessels are going to have beta 2 receptors in them. Okay, what else has beta 2? Well, my smooth muscle that I find in my bronchioles, the little air passages. And so what's this going to do? It's going to inhibit it. Well, why would it inhibit it? Well, if it inhibits it, it causes the muscles to relax. Therefore, the blood vessels get bigger, or the bronchioles get bigger, allowing more blood and more air into it. So again,
muscle to dilate.
Inhibiting is actually not a bad thing. In this case, it's a good thing because it inhibits the muscle from contracting, and so my passageways for my blood or my air get larger, therefore I get more air in and more blood to my skeletal muscles and my heart during an emergency, and that's when I want more blood going there. Now, if you remember from lab, we discussed how the autonomic nervous system was broken down into the sympathetic division and the parasympathetic division. Sympathetic being fight or flight, parasympathetic being rest and digest. Okay, now look at the setup again. Notice that the thoracic nerves had a short extension to the sympathetic ganglion and then a long extension to the organ, whereas the parasympathetic division, the cranial nerves, especially that vagus nerve we mentioned that slows the heart, notice they have a long extension from the brainstem or the spinal cord, and then a very short synapse before the organ. So we got the short to long, long to short. Okay. Notice also, so wherever they synapse is where they're going to be releasing the neurotransmitters. So what we're going to look at next is which neurotransmitters are released at each of these synapses, both from the sympathetic or the parasympathetic. Now, first of all, both of them release acetylcholine, but only one of them releases norepinephrine. So which one do you think releases norepinephrine? Well, obviously it's going to be the fight or flight, because norepinephrine is basically adrenaline. Okay, so norepinephrine is where we're going to find it. But so everything in the parasympathetic, wherever it synapses, whether it's the first long one or the second short one, will be acetylcholine. So that's easy to remember. But for the sympathetic, it's not too hard to remember if you understand that the adrenaline needs to actually be released to the actual organ. Then it's at the organ or gland where the norepinephrine is released. So the synapse before that area will also be acetylcholine. So back here, here's our sympathetic and parasympathetic. Notice we had a short synapse and then a long synapse to the organ, like we just saw in the last picture. Here we have the parasympathetic, so the rest and digest, the fight or flight. Here we have the long and then the short to the organ. And of course, somatic was our motor neurons going to our skeletal muscle. Now, we already know that the motor neurons, of course, the nerve cell bodies, dendrites, are always in the gray matter area. And then here I see this is actually myelinated axons, because it can be long axons and running into the nerves. Here I see a myelinated, but I see an unmyelinated because it's not having to send the message over such a long distance as, say, a somatic. But back to what we're actually looking at here. Okay, what we're looking at here is what neurotransmitters are always released from the somatic. Well, it's always acetylcholine. Okay. What neurotransmitters are released from sympathetic? Now, we know the sympathetic is what's actually going to, where our epinephrine is going to come in. So epinephrine is always the neurotransmitter released directly to the organ. Because remember, epinephrine, we need it to, relax the smooth muscle and the blood vessels going to our skeletal muscle or going to our heart, but we need to constrict the smooth muscle in the blood vessels that's going to our digestive organs. So epinephrine is going to be able to do both of those according to what the receptor is. So this is the only place that norepinephrine is going to be released. Acetylcholine will be released here, acetylcholine will be released here, and acetylcholine will be released here. Let's watch.
Of the somatic nervous system release acetylcholine. They are cholinergic. Skeletal muscles bear NACH receptors. Thus, the action of acetylcholine on skeletal muscle is direct, fast, and excitatory. Click the first sympathetic neuron. The first of two neurons in the sympathetic chain, the preganglionic neuron, is cholinergic. Click the first parasympathetic neuron. The first of two neurons in the parasympathetic chain, the preganglionic neuron, is also cholinergic. The second neuron, or ganglionic neuron, in both the sympathetic and parasympathetic chains, has NACH receptors.
So the only place that we have norepinephrine released is from the sympathetic nervous system